Welcome. My name is John Svensson. I work at Boliden as an industrial PhD student and development engineer. And I work primarily with positioning for I'm going to talk to you briefly about a technology we see popping up everywhere now, which is called ultra-wideband radio, and introduce to you kind of how it works and why we're interested in it. So the first thing I'm going to briefly cover is sort of what is this technology, how it's different from conventional radio, and sort of what it's used for today. And then I'm going to talk a bit about positioning in general, but more specifically about ultra-wideband positioning and how it actually works, and some of the use cases we envision for this technology. But the brief Wikipedia description is that ultra-wideband is a radio that uses short, wide-frequency pulses to transmit large amounts of information over small distances. So a typical radio wave, you have a continuous wave, but you adjust frequency or amplitude. But in this case, you have a large amount of shorter pulses. So we can illustrate this. So dividing radio into narrowband and ultra-wideband communication, on the top here we can see what we call narrowband. And basically you have one continuous wave, but you sort of modulate it. So you can change the frequency and amplitude, but you stick completely to one frequency. With ultra-wideband, you instead send very, very short pulses that cover a large frequency band. And a cool benefit of this is, since you have a very low energy density in any given frequency, ultra-wideband can coexist with other radio technologies without sharing. These pulses are typically in the nanosecond range. So if you use it purely for communication, you can reach transfer speeds of up to gigabits per second. And having these pulses further apart, when you don't get sort of transfer capability, enables you to reduce risks of path sensitivity issues, since the pulses are very unlikely to overlap. Also, you can save a lot of power by having the pulses further apart, since typically in positioning we don't really need to know our position every nanosecond. So if we can know it 10 times a second, that's often enough, and we can save a lot of power that way. So the cool thing about ultra-wideband from my perspective is that if a transmitter both compute their internal delays and use very exact clocks to measure the total round-trip time, you can get a very precise time of flight measurement. So you can estimate the range between two ultra-wideband units down to centimeter ranges. But usually ultra-wideband came up as an alternative to Wi-Fi, actually, and it saw some popularity in the early 2000s, but it never really came through. So there was a thing called wireless USB that used to be based on ultra-wideband, which was used similarly to what we think of Bluetooth today, so wireless peripherals. But it never really took hold. A really cool thing you can do with ultra-wideband is you can make radars that penetrate walls. Since you have a very broad band of frequencies, some of them are always going to come through any given obstacle and bounce off of whatever's behind it. So you can see people through walls and stuff with ultra-wideband. But the primary reason I'm here today is because it's very useful in positioning, since it enables us to get these exact ranges. And it seems to be settling in as a sort of dominant radio technology for positioning at the moment. And in terms of performance, it's somewhere between what we call signal strength-based systems like Wi-Fi and LTE, and visual ones like camera tracking and lasers. So positioning in general, say we have a miner, well-known miner to some, this man, but how do we locate him? So today, some free advertising for my friends here on the first row. This is a product from Mobileye, and basically what we do today is we look at the phones of our employees, and we see which Wi-Fi access point in the mine that phone is associated with. So we do more. We could look at signal strengths and sort of estimate that, but then we sort of lose certainty about our uncertainty. So it's better to be certain about an uncertain result than to be certain about a certain one. So at the moment we're to this, and while it's usually probably in the 50 to 75 meter range of errors, it could be anything up to the maximum range that a phone can associate with a Wi-Fi access point. So in worst case, it could be 150 meters. But ultra-wideband positioning then, instead. So the internal clocks of ultra-wideband it's usually in the picosecond range. So you can use these short pulses to get centimeter precision. And then we estimate the position using multilateration. This is sometimes mistakenly called triangulation, but if you're using distances and not angles, it's multilateration. So we see the distances from several ultra-wideband anchors, and we sort of overlap these circles and out the most likely point for the target we're tracking. But in a mine, that's kind of problematic, since it's not an open area, so we need to consider indirect paths. And we have some extra uncertainty here, since we don't really know exactly what signal path the signal is going to take. It takes sort of the inner curve or the outer curve, for example, and that's enough to sort of reduce this high precision significantly. And we also have another limitation, which is typical in that all our reference points are placed along the signal path. We only get precision along one dimension. Only sort of how far into a mine tunnel you are, rather than a 2D or 3D position. So this is one picture of a test we did with a supplier. Let's not mention too much. Where we had a number of ultra-wideband anchors in Kankberg, and we measured the position of one ultra-wideband tag that was on this guy's head. And these circles indicate the range measured by each of these anchors, and we can see that the ranges all overlap very nicely. And it seems like he was walking on the right side of the tunnel here, so overlapped somewhere around here, and it's probably within the meter range, at least. So what can we do with this? So the first one is what I covered already, just straight up positioning, knowing where our people are for safety, for different types of automation, traffic control, that sort of thing. But we can also make range-sensitive warning systems. So say you have machine-human cohabitation in an area, and you want the machine to slow down when someone approaches or stop if they get too close. So instead of having like a laser just completely shutting it off, you can have a dynamic system or have a warning system for the human saying, now you're getting close to a dangerous area, or you should slow down because there are people moving in your area, etc. And if you add more anchors, you can do, or more tags in this case, you can do some interesting things. So you could estimate the pose of a person. So say you have an anchor in the ceiling that both of the tags attached to a person, say the head and are on the same distance, you could assume that the person is lying down, for instance, and you can detect sort of dangerous situation that way. But also in automation, you can estimate the orientation of machines. So one of the things we're thinking about is having a loader load a truck in the mine autonomously by using ultra-wideband to sort of estimate distances between the two machines. And if you add more anchors, you can have 2D or 3D positioning where you need it. So say you have a large workshop and you want to know exactly where something in 3D space, say drone flight or something, anything really, you can do that by adding more anchors. So summarizing this, and then we can do some questions if you have them. So the first thing that's good about positioning is the high precision. That's really the selling point that enables all of these things. And this is sort of an enabler for ultra-wideband to sort of sneak in. You don't need to just replace everything. You can just sort of add ultra-wideband to what you already have, since it doesn't interfere with other radio. It doesn't use much power, so you can actually have battery-driven tags. Especially for positioning, since, as I said, we don't need to know the position of our target every 10 nanoseconds. We can do it a second or every 1/10 of a second. You can use it for communication, so you have a redundant communication system if you need it. Currently, there is no fixed standard for ultra-wideband communication, so you can't really have a network and then plug and play different units to it, but it's there if you need it for safety or something. And what's popped up is that the current selling points, which is scalable and doesn't require large investments, is this sort of these safety features, these range-dependent safety features. But there are some downsides, though. So say you want to use this for positioning. At the moment, that means you have another layer of infrastructure in your mine. So you have a full communication network, and then you need to add this on top of it. So we're hoping that in the future we'll be able to buy communication infrastructure that also includes ultra-wideband for accurate positioning. If you want to get anything more than 1D, you're going to need a very large amount of anchors. Since you have this problem with overlapping circles, but when they overlap, when they're at a distance, you only get this sort of, the overlap is quite wide. So if you want to have 2D positioning on a road or 3D positioning in a space, you really need to have quite a lot of these. But that's true for any range-based system. And also, we're not exactly sure how we're going to deal with cases where we don't have line of sight. So it adds some ultra-wideband is very certain when we know we have a direct path. But if we're unsure about that, then we might misinterpret some data. But it's better than signal strength-based systems anyway. But we're not sure exactly how much uncertain we get from that. Yep. So any points or questions? Yeah. So are you referring to why it's popping up now? It's popping up here. I mean, some telecommunications companies are starting to produce ultra-wideband services, but a lot of the things we're hearing are from universities. Like, people want to research this. They think this is the big new thing. So at the moment, I don't see that many complete solutions available, but it's sort of, it's almost there, and it's coming for sure, as you can tell. Bandwidth is easier. On short ranges, you can have gigabit speeds, gigabits per second. Ranges, it's a bit more tricky. It depends largely on how you design the units, but the one tested in that you can pretty much reliably see them up to 60 meters at the power ranges we've been having, but often they'll pop up further than that as well. But if you increase the power, you can probably increase that quite a lot as well. Okay, anything else? Okay, I think I'm done.